गुड इवनिंग फ्रेंड्स, स्टडी विद अपाला इंजीनियरिंग एंड जनरल जियोलॉजी परवीन सिंह बुक। तो हमारा चैप्टर 20 चल रहा था और उसमें है मास मूवमेंट। मास मूवमेंट को हम लैंडस्लाइड भी कहते हैं। ठीक है, तो अभी हम लोग पढ़ रहे हैं कंपोजिशन ऑफ द मास। तो some materials are stable in a given set of conditions of slopes and water contents, whereas others may be practically unstable under those very conditions. And crystalline igneous rocks like granites and gabbros and massive metamorphic rock like marbles, quartzite and gneisses may be stable even with vertical slopes, where the same cannot be said about chalk, soft varieties of limestones or shells or clay stones or soils. It is therefore obvious that fundamental characters that is responsible for the stability of mass is its composition, which has both chemical and physical implications. By composition of the mass is meant in the present study whether the mass is in the form of soils or a rock, if soils whether it is cohesive or non-cohesive, and also if it is sandy, silty and clays, or a mixtures of two or more of these components. If a rock, whether it is an igneous or sedimentary or metamorphic rocks, and also within each group to which particular class it belongs. The role of composition of mass in its stability becomes important because a broad assessment can be made about the stability of a mass if its an exact composition in both physical and chemical sense is known. Thus, sandstones, for instance, occur in a great variety of types of fine textured, dense and massive sandstones with the siliceous cement may be very stable even at vertical slopes, whereas the same rocks with the ferruginous, calcareous or clay cements may become unstable at angle of 60 degree or even less. Along with the composition, the texture of rocks and soils masses play an important role in their stability. Texture indicate the size, degree and manner of packing of the constituent crystals or grains in a rocks or soils. As such, it controls the porosity and permeability of the mass, two very important characters controlling the infiltrations and percolations of water through the mass. Thus, other things being same compact, dense and impervious rocks are more stable than loosely packed, porous and permeable masses under similar conditions. Geological structure are of great significance in defining the stability of mass, especially in the rock. These structures may be divided into three classes: the bedding planes in stratified sedimentary rock, the schistosity, foliation and cleavage in metamorphic rock. The jointing structures, fault and shear zone in all types of rocks are fissure in the consolidated clay. Relationship of each class of these structure with the stability of mass has been discussed below in essential outlines only. The bedding planes, many sedimentary rocks are layered or stratified, and thickness of layers may range from a few centimeters to many meters. The bedding planes, the surface between any two adjacent layers is a planes with the least cohesion in such a layered mass. In their natural depositions, these layers may be horizontal, inclined at various angles with the horizontal dippings, or even verticals. The dip of the stratified rocks exert very important influence on the stability of slopes. This may be explained in different cases as follows. Case 1. The layers are horizontal dip means 0 degree. As such rocks forming the slopes of the natural valleys and artificial cuts are stable at all the angles up to 90 degree. Whence they fail, it may be due to presence of secondary jointings or related fractures. Case 2, the layers are inclined in such a situations, assuming that the rock is free from any other type of discontinuities, joints, shears, and fault zone. The stability of slopes, natural or artificial, will depend primarily on the conditions whether the layers are dipping backward into the mountains or forward into the valleys or the cuts. So A horizontal layers, nearly, B inclined layers, inclinations of layers as versus stability. So when dipping into the valleys, and second, how was the tendency of the layer to slides get a free play, and the slidings may take place where the dip of the layer is greater than the angle of internal frictions, degree 30 degrees, and the slope angles beta exceed the dip angles gamma, alpha, sorry, beta, gamma. It I confuse. Small lambda. The safe height of for a vertical cut on this types of face can be fixed only after proper evaluations of the force tending to produce failure and those available for resisting the failures. Anchored parallel to dip of strata, anchored parallel to strike of strata. तो उसके अकॉर्डिंग इसका डायरेक्शन तो दिया हुआ कि अगर जैसे कट है तो उसके डायरेक्शन में डिप कैसे हो रहा है स्ट्रेटा, इसका इस डायरेक्शन में कट है तो इसका इस डायरेक्शन में डिप होगा, ऐसे कट है तो इसका ऐसे डायरेक्शन होगा. So the dip factor has to be kept in mind whilst giving cut in stratified rock. It may be possible to explain now that cuts parallel to the dip of the rocks are more safe and stable compared to those parallel to the strikes of the layers. It is because in the first case the layer do not dip into the cut, whereas in the second case rocks do dip into the cut on one face. It is this face which is more prone to sliding. The condition of stability is further endangered when rocks dipping towards the valley are interstratified with layers of weaker materials such as clays or cell. These weaker layers provide potential planes for failures due to slidings for the entire mass resting over them. The metamorphic structures, cystosity, foliations, and cleavage structure as found in metamorphic rock like schist, gneiss, slate, respectively, all behave as surface of weakness and promote the failure. This is primarily due to the fact that in most cases, weathering deteriorations in these rocks take place along these planes, making the contact quite vulnerable. In metamorphic rock derived from stratified sedimentary rock slate, the direction of cleavage with respect to the original beddings may cause complex systems of weak planes, as such slip may be of a common occurrence in the slopes made of the above metamorphic rock, and especially so when these structures are inclined towards the free side of the slope. The jointing structure, joint of any types, are always to be studied with great caution in rocks making slopes for rock. Two reasons. Firstly, very few rocks are free from these structures which may occur due to tensional compressions or shears to which these rocks have been subjected since their formation, and secondly, they occur in sets or groups affecting the rocks from the surface to considerable depth on macro or micro scales, but eventually reducing the shear strength of the mass considerable groupings and above all inclinations with respect to the free face of the slopes. That is given great importance. Joint set profusely is developed in a mutually interesting fashion, one set being inclined towards the free sides of the slopes are given first importance in the stability analysis. In all types of rock slopes and falls behave similar to joints and beddings planes, except that they are generally on macro scales and amenable to rock treatment and solution. Shear zones are most potential surface for rock slip, especially when lubricated with waters due to the soft characters or the shear zone materials. So this is important diagram, some geological structure favoring slopes failures. External factors. An analysis of many slope failures make it clear that in quite a few cases an external factors might have triggered the slide, whereas in other cases it might have been one of the causes contributing towards the failures. Among the first category of factors are included vibrations from artificial and natural phenomena. A mass purchased on the slopes may be stable, but critically the gravitative forces have not yet overcoming its frictional resistance. A slight vibrations or jerk to the mass may be sufficient to disturb this equilibrium and the mass becomes unstable. Such vibrations are easily available from heavy blastings, which may also cause fracturings much beyond the rock's volume to be blasted out, and heavy traffic on hills roads and repeated failures of many hills slope may partially be due to the cumulative effect of such vibrations. Vibrations due to natural causes such as earthquakes often initiate mass failure on a large scale that may continue much after the quake. The Assam earthquakes of 1897 produced some of the gigantic landslips ever observed in the region. Another important external factors often overlooked in the removal of the support at the foot of the slopes, as during excavations for road widenings and without due regard to the critical conditions of the stability, the slopes that might have been previously stable becomes hazardous after such an excavations. A similar cause for slope failures in loadings and critical region of slopes from above. It is also common exercise during highway construction in hilly region. The stress due to this additional loads add to the stress due to the mass of the slopes. The resulting stress may have a different radial dispersions intersecting with the free slopes and facilitating failures. Removals of vegetables cover, especially tree deforestation, is the third external factors that has been contributing factor in causing slopes failures in a large number of cases, including the notorious Nourish slide near Ramban on National Highway 1 in Jammu Kashmir. Thank you. Please give a positive response. Thank you.